Thanks to Brilliant for helping support this episode. Hey crazies, a black hole is what you get when you cram matter and light into a small enough space. The outer edge of that space is called the event horizon. It's the ultimate in compactification. Nothing can escape it. But wait, the universe used to be really small, right? If we imagine time in reverse, there must have been a moment when all the matter in the observable universe was compressed that much. How did the universe escape? This episode was made possible by generous supporters on Patreon. So, the size of a black hole, at least a non-rotating one, is given by something called the Schwarzschild radius. Schwarzschild? Whatever. It's named after my buddy Carl, who found the first exact solution to Einstein's equation. Seriously, he was a total bamf. Anyway, Carl's radius for a black hole depends on one thing: mass. Well, technically energy, but that energy becomes mass inside the black hole. The point is, all you have to do is plug in a mass and you get out a radius. You get the size of whatever black hole that much mass would make. It tells us we'd have to cram the Earth into a space this small to turn it into a black hole. That's a tiny amount of space. Of course, it's impossible to do this with the Earth, but it is possible with masses a few times larger than our Sun. It takes that much gravity. The observable universe has more than 3 suns in it, right? Oh yeah, a lot more. If you plug the total mass of the observable universe into Carl's radius, what you get is 528 billion light years. What? That's over 10 times the size of the observable universe. Could the universe actually be inside? No, don't be ridiculous. The observable universe is not inside a black hole for one very important reason. This calculation is bull nuggets. You can't just plug numbers into an equation and be like, this means something. Carl's radius requires that mass ball be surrounded by comparatively empty space. You know, somewhere to escape to, successfully or not. That's true for a planet. It's true for a star. It's even true for this black hole. But it's not true for the universe. There's no empty outside to escape to. It's the same uniform universe everywhere. That means this doesn't apply, which means this number is completely meaningless. Like I said, bull nuggets. The universe is not inside a black hole, so it doesn't have an event horizon. Or does it? An event horizon is just a boundary beyond which we cannot observe events. The universe does have a boundary like that. It actually has 3 boundaries that we call horizons: the cosmic event horizon, the particle horizon, and the Hubble horizon. But to understand them, we all need to be on the same page about the universe. Space is expanding, and this makes distant galaxies recede from each other. The farther away they are, the faster they're moving away. But that animation grossly understates the scales we're working on here. Galaxies this close could easily be moving toward us rather than away. In fact, our closest neighbor Andromeda is moving toward us. It's on a collision course. It'll hit us in a few billion years, and put on quite a show for a few billion more. When we say galaxies are moving away from us, we mean galaxies in other superclusters. This is much closer to the true scale of the universe. Individual galaxies are too small. Each point of light is a cluster of galaxies. Those clusters form superclusters that collect into giant filaments. But without some basis for scale, this looks more like a zoom than an expansion. So we'll go back to the individual galaxies. Just keep in mind that it's not to scale. The universe is big, like really big. Mind-bogglingly big. It's so big that the recession speeds of some galaxies can get out of hand.
The Hubble horizon!
This is where galaxies are moving away at the speed of light. It happens at about 14.5 billion light years from us, just a little past the 13.8 billion you might expect given the age of the universe. Any galaxy farther away is receding from us faster than light. Fast! But we can still see them, so the Hubble horizon isn't really a horizon. It's just where things start to get weird. Light from beyond it can arrive on Earth, as long as it's not coming from too far beyond it. See, the Hubble horizon grows, so it can catch up to some of the light, allowing us to see it. The limit of our vision is a little farther away.
The Cosmic Event Horizon!
Nothing that happens outside this horizon will ever be seen by us. Ever. It's located about 16.7 billion light years away, just a little past the Hubble horizon. Now, you might have heard the observable universe is a lot bigger than that, and it is. Remember, measurements get real weird beyond the Hubble horizon, and that's because light takes time to get places. If light is emitted from just inside the cosmic event horizon today, it won't arrive on Earth until the distant future. By then, those galaxies could easily be beyond the event horizon. It works the other way too. If we're receiving the light now, it was emitted a long time ago. It could easily have been emitted when a galaxy was inside the event horizon. By now, it's beyond the event horizon, but we're still receiving the light from when it wasn't. So how far away is the farthest stuff now? Pretty far.
The Particle Horizon!
This represents the limit of our vision, the current size of the observable universe. It's 46.5 billion light years away, a whopping 3 times farther than the other two horizons. This is how far away from us anything we've ever received light from could have gotten since the beginning of time. It's the current location of the farthest stuff we can see, the hydrogen plasma that emitted the cosmic microwave background. Mind you, it's not hydrogen plasma anymore. It has since collected into galaxies. But we don't get to see what it looks like now. Remember, it's way past the cosmic event horizon. We only get to see what it looked like 13.8 billion years ago, because that's when the light was emitted. Back when the particle horizon was inside the cosmic event horizon. You know, we could actually graph this out across time if we use models. The Hubble horizon, that place where galaxies are receding at the speed of light, is always the closest horizon to us, because it isn't really a horizon. It just separates the familiar physics from the weird physics. The cosmic event horizon was the farthest of the horizons in the early universe. Unfortunately, as space expanded, the particle horizon overtook it pretty quickly. Where they cross is the most recent state of the particle horizon we'll ever get to see. But the light from back then has been traveling through expanding space. So as the particle horizon approaches the cosmic event horizon, the light takes longer and longer to get to us. It'll actually take an infinite amount of time to see what happened when they crossed. Cosmology is so weird. In the present, the Hubble horizon is 14.5 billion light years away, the cosmic event horizon is 16.7 billion light years away, and the particle horizon is 46.5 billion light years away. I know, these numbers are ridiculously big, so if it helps, ignore the billion. Measure the numbers in gigalight years and gigayears like I do. It'll help make the future of all 3 horizons a little less overwhelming. Anyway, let's go back to the cosmic web and see what this all actually looks like. The cosmic event horizon starts out the farthest, but is overtaken by the particle horizon within a few billion years. This is what they look like now, at 14.5, 16.7, and 46.5 gigalight years, respectively. Eventually though, the particle horizon will expand way out of view. The Hubble horizon and the cosmic event horizon will settle at about 17.5 gigalight years, trapping us in a bubble forever. It might not be a black hole, but it's still definitely a trap. At least until we invent some kind of FTL drive. But the weirdest part of this whole thing is that we can see galaxies that are already beyond the cosmic event horizon because their light is old. All the galaxies you're seeing in this deep field image are just ghosts from the distant past. And that's what they'll always be. Forever. The cosmos is terrifying. Oh, so, got any questions about these cosmic horizons? Please ask in the comments. Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to keep up with us. And until next time, remember, it's okay to be a little crazy. Do you want to learn something new? Well, Brilliant is the place for you. It's a website and app that makes learning accessible and fun. Brilliant's approach is based on problem solving and active learning. It's all about seeing concepts visually, interacting with them, and then answering questions that make you think. There are no tests or grades, just pick a course and get started. If you make a mistake, no big deal. Just check out the explanations and learn from them. With over 60 courses, there's something for everyone. Train yourself in basic logic. Learn to code. If you want something more advanced, try out differential equations or neural networks. If this sounds like a service you'd like to use, go to brilliant.org/Science Asylum today. The first 200 subscribers will get 20% off an annual subscription. Thanks to everyone who tried to help me pronounce Ramon Cajal? I'm sure I'm missing a sound in there somewhere. Anyway, I guess this Ramon guy is a pretty big deal in the neuroscience world. The Socratica channel has a video all about him if you're interested. Link in the doobly-doo, and thanks for watching.